Good afternoon, all. Let's start the class. I think yesterday we discussed about the Zener regulator. Before we start and before we do the next session, we can have some kind of exercises regarding the Zener regulators. I'll share the screen and you can try this question. This is some kind of extension of the yesterday question. You can try this one. Take a couple of minutes and try to solve this one. And after that, we can have a discussion regarding the other parts of the Zener regulator. Okay, we can do it now. Actually, the circuit is, this is the circuit. It's not difficult circuit. This is load. Okay, those are the things we know the more. Okay. Yeah. This VL, load voltage. This is load voltage. We know that over the time, low voltage should be center voltage. Okay. Then we have to find this incoming current, center current, and load current also. Okay. The maximum center current we can calculate because that we know that center is, this one is 2 watt center. And we can find the maximum center current. This is 2 watt divided by 12 volts. Then it is nearly 167 milliamperes. Okay, then this is the maximum center current. Then then at no load, the center can send this much of current. Then the minimum current, the RL max, when RL is having the maximum resistance, then we can find the load current, minimum current. This IL, we can find when RL is 2 kilo ohm, then IL is 12 volts. Okay. $6 million. Okay, during that time, what about the Zener current? At that time, IZ is IZ max minus IL. And this is 167 and this is 6, then 161 milliamperes. Then when the load is having its maximum resistance, the Zener current is 161 milliamperes. Okay. Then the load RL is 500 ohms. Then IL is 12 volts. Into 500 ohms. And 24 milliamperes. Then we can find IZ at that time. Then these two are within the range. Then Zener can handle this one. Okay, here, then to find RS resistance and what is the voltage across RS? VRS is VS minus VZ. VS means it's 18 volts, VZ 12 volts, then 6 volts. Then based on that, we can find RS. VRS divided by IZ max. This is 6 volts. IZ max. How much? 167 milliamp. Then is it okay? Okay, Then one thing I think we have to understand well, I think you know about this one well. Uh, you know that characteristic curve of Zener diode. This voltage and this is current. One and in the reverse side. Okay. But actually, if you consider this one, that for example, this is Zener voltage VZ, and this is VF forward voltage. This is Zener voltage. But you have to find with the Zener voltage also, the Zener diode also that okay, wait, I'll show you a practical Zener diode graph. The Zener diode should provide that some kind of linearity over the Zener region. Wait that until I find sheets. Okay, anyway, that it will take some time, I think, for the moment. I'll draw this one, but if I draw this one, maybe this part. Is something like this. And assume that this is the center region, then the reverse bias mode is coming like that. And after that, here we can find this is V, and we can consider this point as the center one. And in this region, you can see it's very much close to this one. Then we can take this point as.
Excuse me, sir.
Yes.
So we can't see the screen clearly.
You are seeing that the previous screen still?
No, sir. Something on the word. I mean, black screen. Can you reshare the screen, sir?
Okay. Now can you see?
Yes, sir. Now we can see.
Then here you can take this one as center voltage. You can see after that, and during this region, the center voltage is almost same, very much closely same, but in this region, in this area and after this point, it's not linear. Okay. Then here at the, then because of that, we can take, sometimes I am putting some kind of figures here. This may be 10 milliampere and this may be 80 milliampere minus. Okay. Then when you take some kind of, then when you send some kind of currents through center, then when you send 10 milliampere to 80 milliampere within this range, center voltage is fixed. But less than 10 milliampere and greater than 80 milliampere, then center voltage is not fixed. But again, that voltage fluctuation, voltage variation may be there. Then if you are going to use this one as voltage regulator, but the best region is this. Okay, here in the previous one, I'll show you it again. This one that we have calculated that the center current is this. When the load is varying, we have calculated two center currents. I said 1 and I said 2, 143 and 161. This is 161. This is 143 milliamps. But we have calculated that one. We have decided to operate this center within this region. But before that, we have to make sure that by looking at the graph, we have to make sure that this center is this one. This one is in this region, and in our case, that what are the currents? 143 and 161. Then it may be here. This is 161 and this is 143. But the actual linear region may be this. It may be, we can take this 50 milliampere. This one may be 180 milliampere like that. Then this region is okay. If your design is falling within this region, then your design is okay. This one. Otherwise, that if your zener current is moving out of the range, it's not linear. Because of that, the zener voltage may not be fixed. It may be varying. Okay. But I am telling you that when we do a design, that we have to be careful. We have to consider this one also. Okay. But in your question, that you might not have the type of difficult parts. But anyway, that within this region, we have to use our zener diode as a regulator. Okay. Not in the entire region, the zener voltage is linear. Zener voltage is fixed. Okay. Then any question regarding that zener regulators? Zener regulators, that's what we want to know. Then I think we can remember this one. If you input this type of waveform to this diode, what is the output? Something like this. Okay. Then what about that if you input this type of waveform to this one? What is the output? Diliti, that how did you ask the question, how did you get 50 milliampere and 180 milliampere there in the graph? But actually that in the previous one, I think you mean that previous one. Here, this one. Yes, I have taken that one. But considering that range may be falling into this, this may be the minimum value, and this may be the, by assuming that this may be the minimum and maximum value within the linear region. Assuming that, but we have to prefer data sheet or in the question that we have, that we should be received that. Otherwise, we don't know. I assume this one. This is min and max value. Okay, here that if you give this type of waveform, what is the output? Nothing will come. Why? It's a reverse bias. Sorry, the other way. This negative half cycle will come here. Okay. Then okay, what about that if you have this type of circuit? Now you are giving this one. It's not normal diode, it's standard diode. Now what's the output? During the positive half cycle, what will happen? It can go normal. During the negative half cycle, the diode will be reverse biased. But diode can be reverse biased, and then the reverse bias, through a reverse bias diode, there is no current. But after increasing this voltage value, after the reverse voltage value, when it increasing here, then sometimes this is the VZ, and here this may be VZ. After that, it starts conducting. Whatever the voltage here, we can see this gap will be here. Until it comes to the center voltage, we don't see anything at the output. But after receiving the center voltage and going beyond the center voltage, that part only will be received at the output. Is it okay? Did you understand it? Yeah, actually, Rishabh is asking questions. Isn't center voltage is a fixed value? Yes, Rishabh. I know that. What do you think? Yeah, but anyway, that after a certain period of voltage, that the center is going to increase that one. You know that. I know that. What you mean that here you are asking that this center voltage is fixed because of that. Here also that we cannot have the voltage like this. But anyway, it depends on the current. Okay, for the moment, okay. Can you think about that one, this type of circuit? What do you think that when you have this type of circuit, you have this sine wave input and your circuit is something like this. But what about this positive one? This one? Then assume that here this is VZ. On this side, this waveform, this one can come up to VZ. At VZ, it will be cut. Why? At this point, the voltage is slowly increasing. It's 0 to VZ. Until 0 to VZ, there is no problem because this is reverse bias current. There is no current going through it. But after that, you can consider the Zener will not allow to increase the volume beyond VZ. Then this is VZ. Okay. After that, then what will happen? The negative half cycle is coming. When the negative half cycle is coming, the negative voltage, that voltage is applied from the anode terminal of the Zener diode. Then diode will be forward biased. When the diode will be forward biased, then you can consider the whole current, whole voltage can go to the other side. Then across these 2 points, what can we see? Only 0.7 volts. Okay, then the gap between here is 0.7 volt. Then total voltage here to here. This voltage is VZ plus 0.7 volts. here that actually I draw this one, but we have to put a diode in a circuit, then only we can exactly do. Okay, what about that if we have a circuit like this? Again, we apply sine waveform here. Now this time, okay, now think about this one. Is it okay? You do it. Okay, how can we do that one? Because of this Zener diode D2, assume that this is Zener voltage V is it V2. This is Zener voltage is V1. Assume that one. Then how can we draw the waveforms which in V? This is our output waveform, and our waveforms will be like this. Okay, then this is V2. This is V1. Due to the D2 diode, when D2 diode is reverse biased, the positive half cycle will be clipped. And when we consider the negative half cycle, the D1 diode will be reverse biased. And when it comes to this V1 Zener voltage, then that one will be clipped. Is it okay?
Excuse me, sir. Excuse me, sir.
Yes.
Sir, in there, don't we have to assume the forward bias 0.7 for both negative and positive?
Now, there are actually that here in this case, the actual case that actually we have to consider this one should be added to that one. Exactly, you are correct. And this should be added plus 0.7 and plus 0.7, like that. Okay. Assume that this Zener is 5 volts and this is 5 volts. Then this voltage is, this is 5.7 minus 5.7 volts. This one is plus 5.7. Yes, you are correct.
Thank you, sir.
Is it okay? All of you are okay with that? Okay, if you are okay that we can finish this one. Actually, we call these type of circuits are clip-in circuits. These are Zener diode clip-in circuits. It can clip the voltage. That if you want to clip the voltage at a certain point, then you have to select carefully suitable Zener diode. Then beyond that point, the voltage will be clipped. Then can you try this one? Sorry. It's not Zener diode. It's normal diode. Try these two. here, that positive, when you receive the positive cycle, and this diode is reverse biased. Because of that, there is no path to go to the current that way. Because of that, the entire positive half cycle will be received. But when the negative half cycle is applied, the diode is forward biased, then this 0.7 volts part will be there. Then after that, this will come. And here we have this 0.7 volts gap. In this case, the positive half cycle will be clipped. It will be short circuited. We short circuited, and we will get only 0.7 volts during the positive half cycle, and negative half cycle will be received. Why? For that one, it's reverse biased. Likewise, this one will be, these are the waveforms, these are the resultant waveforms. Okay, any question? Anything? Okay, these are the diode clipping circuits, and you can use normal diodes and Zener diodes for the clipping circuits. Any question? Anything? Okay, if you don't have any question, then we can start a new section now. Now you know that when we combine P-type semiconductor and N-type semiconductor, we have PN junction. Then it's a junction diode. Okay, you know all about those things and how this junction is behaving, and after that, to operate that junction, what are the things that we have to, what type of voltage you have to provide. Then after that, we can make a diode. Then you know the diode characteristics, and when you apply forward voltage, that how it's operating and how it can provide current, how it can allow that forward current go through it, and when it reverse bias, then you know that how it is operating. And after that, we have discussed about the diode applications also. The common, very famous application is diode as a switch. The second one is we can use diode as a rectifier. Then full wave rectification and half wave rectification is there. And we have discussed this one also. And also the switching action we can use for protection of some kind of circuit. Okay. And those are the applications. And when it comes to that special type of diodes, we have discussed about LEDs. But LEDs are not like diodes, especially developed to emit lights. Then we can use those things for the indicators earlier. And this time also that still we are using those things in indicators. In addition to that, we're using those LEDs to make bigger screens and also for lighting applications. Okay, then the different voltages should be applied to the different type of LEDs to turn it on. And starting from 1.2 volts, nearly red, and it may be 2.4, 2.6 like that for the green and amber color. But anyway, you can consider generally it's 2 volts or 2.2 volts, and normal LED can allow go through current, that forward current. It may be ranging from 10 to 30 or 10 to 50 milliampere, depending on the type of design. In addition to that, the special type of two light emitting diodes are there. That's a blue color one and white color one. To operate that one, we have to provide more than 3 volts. After that, we discuss about Zener diodes. Zener diode is a special diode specially designed to operate in the reverse bias mode. Then we call that the Zener region. The Zener region, that Zener voltage is there. After applying beyond the Zener voltage, diode will not be damaged, and we can use that action for different things. And we can use this Zener diode as a voltage regulator. It's a simple voltage regulator. If your power requirement is not much more bigger power requirement, for simple power requirements, for normal power requirements, you can use this Zener diode regulators, okay, to regulate voltages. Then in addition to that voltage regulation application, we can use these Zener diodes for voltage clipping. Again, it's a very simple circuit, the voltage clipper circuits. And we can use this voltage clipping circuits for various applications. And when you want to clip your voltage at a certain point, a particular point, then you have to carefully select the Zener diode voltage, considering your voltage, clipping voltage value. So all the time, it's clipping voltage, the Zener voltage plus 0.7 volts will be the clipping voltage. Okay, anything? If you don't have any question, then we can continue this one. This is IC voltage regulators. When it comes to IC voltage regulators, it's not like a previous Zener diode voltage regulator. It's a kind of special developed IC, means integrated circuits. The chips are there to do the voltage regulation. The very common IC type is a 78 series. Series the positive voltage regulators. Okay, this IC is something like that. I'll show you a data sheet. Okay, you can see this one. This is the voltage regulator. Is LM 78XX. LM means Texas Instrument is the IC manufacturer. This is 3-terminal positive voltage regulators. You can see that the typical application circuit, and this one is the common one. Okay, wait, that I'll show you that IC package. Okay, this is something like ICs look like this one. It's always this one. We'll check internet for an image. 7805 voltage regulator. Okay, then share. You can see these images. Okay, this is the IC. And 7805 regulator means if it is 7805, it will be 5 volts regulator. Okay. So this is the input terminal, and this is ground terminal and output one. Very simple application circuit is here. Then this IC is 7805. This will be plus 5 volts one. If it is 7809, this will be plus 9 volts voltage regulator. And likewise, the 7812 is 12 volts voltage regulator. It's a 3-terminal IC. If I draw the circuit diagram, it's something like this. This is input terminal, and this is output terminal, and this is a common terminal, this one. This is the input, and this is the output terminal. This is 0 volts. This is 0 volts. This is the positive voltage we have to give. And this one is fixed 5 volts output is there. This is pin number 1, 2, and 3. And you can have anyone, you can make this circuit. It's a very simple circuit, but to have a smooth operation of this one, then you have to use two additional capacitors here. Okay. And those capacitors are also not very much expensive one. We can have the very small value of these things. This may be 0.1 microfarad, and this may be 0.22 microfarad, like that. Then this may be very simple circuit, and from this point you can receive 5 volts, maximum 1 ampere current. Okay, this side you have to give, I'll check the data sheet, and maximum voltage you can give here 35 normal voltage, 5 volts. Be in 40. This one you have to give maximum 6 to 35 volts DC to this point. And when your power supply is providing 6 to 35 volts as the input voltage, this IC can provide output 5 volts fixed at 1 ampere. Okay. But if you change this IC, maybe if it is 7805, it will be 5 volts output. As I mentioned earlier, if it is 7809, 9 volts output will be there. If it is 7812, 12 volts output will be there. But you can put to this type of things, this type of small circuit to your the cheap voltage power packs. Then your output voltage will be fixed. Then you will have a regulated voltage power supply if you add this one to your cheap power pack. Inside that power pack, there is no voltage regulator, as we discussed earlier. It's only transformer and maybe the couple of other the diode, the bridge circuit, and maybe the current capacitor. Okay. But in case that if you don't have transformer type power supply, that these days that we much more we are having that switch mode power supplies. Inside that switch mode power supplies, there is no transformer, but most of the switch mode power supplies, they are regulated power supplies. You have seen that if you have dismantled this power packs, the normal ones, the lightweight power supplies, the few components are there. It's a switch mode power supply, but very cheap one, but not reliable to power up very sensitive, very expensive devices. But if your device is very expensive or if it is sensitive, then you have to spend a little bit much more money to buy a good switch mode power supply with regulated power supply. Then your device will be safe. And like this one, then we have negative regulator ICs also. The 78 series is the positive voltage regulator, and this 79 series, they are negative voltage regulators. It's fixed negative voltage regulators. Negative voltage regulators, but the same thing, the same type of diagram here also we can see. I'll show you that the diagram 789 series. This one. So pin connection is a little bit different compared to the previous one. Here is the pin number 1, 2 is the ground pin, and 1 is input, 3 is output. In this one, the 7905, this is 1 is the positive ground, and second one is the input one, third one is the output pin. Okay, the application circuit is also same as the previous one. This is ground pin, this is V out, this is V in, 0 volts, this is minus voltage, and if this one is 7905, from this point we will receive minus 5 volts, this is 0 volts. Here also, for the smooth operations, we have to put 2 decoupling capacitors. Like this, maybe 0.1 milliamp. And like previous one also, that here if you use this one, and this is 7905, it's minus 5 volts. Likewise, if it is 7912, it's minus 12 volts. If it is 7918, then if it is minus 8 volts, like that, all are providing 1 ampere maximum output current. You cannot exceed this one, then if you are going to exceed this one, IC will be damaged. The maximum rated current is 1 ampere. These two are very simple circuits, but if you want to go beyond 1 ampere, then you have to have a different type of IC. Actually, I am not going to discuss all these IC type regulators, but you can search the internet and find different type of one. For example, LM317 is 5 ampere type, LF337 is a 5 ampere output variable voltage regulator. Then you can vary your voltage. Then you can have a controller. Then you can change the voltage according to your requirement. It's not like this type of fixed regulators. Those voltages can be varied. If you use variable voltage regulator, it will be very useful. In your case, that if you are really interested, that I'll give some kind of numbers there. You can check those things. But this is LM317, LM338. Those are this is 1.5 ampere. This is 5 ampere. They are not fixed voltage regulators. They are variable. Voltage regulator ICs. You can check the web and download the data sheet. And likewise, you can make a very simple, again, this one is also very simple circuit. You can make those things. Okay, those are all about regulators. And we have started it from diode. And after that, we came to the Zener voltage regulators. After that, for the continuation, we have discussed about the IC voltage regulators also. Now we have ended up the diode section and the voltage regulator IC and the Zener diode voltage regulator section. And next thing is we have to discuss about transistors. Up to this point, that is the end of this part. Any question regarding those sections? And if you are really interested, that I will give some kind of standard Zener voltages also to you. This one. And you can later on, you can refer those things and if you are really interested. Otherwise, that these things are not very much important things. This is for your information, the additional information. Those things will not be coming to your examination. Because of that, there is no problem. It is not necessary to remember these things by heart. I am giving these things for your information. And these are the available Zener voltages. And we cannot have the different type of voltages. And these are the standard Zener voltages. Any question? Anything? Okay, if you don't have any question, now we can finish this class for the moment. We will have a small break. After that, we can start the next session. Okay. Shamat, are you there?
Yes, sir.
Okay, when can we start next session?
Sure, sir. We should log and stay or
I'll stop this one. Then we will have that the break for this video. Otherwise, that the video will be 4 hours lengthy video. Because of that, we break this one. After that, you can log into again after having certain break. That how many minutes? How much of time do you need?
4:20. Can we start?
4:20. We are joining to the same link, or shall I provide a different link?
Sir, if it's good, sir, you can send me the link. Otherwise, I have to call to the institute and get the.
I'll send the link. Okay.
Yes, sir. Thank you, sir.
Okay. Thank you, Shama. Okay. Stop now and shall we meet again 20 minutes time.